Yeah, I hear you. All right, so talking about problem number 1, we have the displacement of a particle at t equals 0.25 seconds. The expression for the particle's position is x is equal to 4.0 meters times the cosine of 3.0 pi t plus pi, where x is in meters and t is in seconds. A, the first part of this problem is asking you to determine the frequency and the period of motion. Well, looking over this problem, the first thing we're going to do is we're going to apply the concept of simple harmonic motion to it. X is equal to x max, which is also referred to as the amplitude, sine omega t plus phi. And mind you that the cosine and the sine are obviously different operators, but the terms on the inside are still going to be the things that we're dealing with, excuse me. So, with that in mind, I can see that the natural frequency is going to be equal to 3 pi. I know that the natural frequency is related to the linear frequency in that 2 pi times the linear frequency is the natural frequency. So that means that if my natural frequency is 3 pi, my linear frequency is going to be, well, divide that out, and I'm left with the frequency is equal to 3 over 2. Leaving it as 3 over 2 is not an issue. So feel free to leave it that way. Don't bother to change it. Okay? So that's the first one. We know that the frequency is 3 over 2, which would be 1.5 or 3 over 2 hertz. Now for dealing with the period, we know that a relationship between frequency and period is an inverse relationship. So all I have to do is create an inverse relationship. I've got this value here. So all I'm doing is solving for t. So I'm going to flip that and flip that, and I'm left with 2/3, and that's a second. So that's the first part. Okay, now looking at B, the amplitude of motion. So this is just simply referring to, once again, our simple harmonic motion. The amplitude is the leading term. So my amplitude is going to be 4.0 meters. The phase constant, this one is slightly more tricky. We would like to say that our phase constant is phi, but it actually is not. We are left with this relationship between cosine and phi and sine and phi. So if you think about it this way, if I evaluate my term so that I'm dealing with maximum possible values, then I'm going to be left with basically 4.0 times that, which would be 1 plus cosine of pi is equal to, now if I evaluate that at maximum terms, I'm left with 4.0, 1 plus the sine of phi. So I'm left with the cosine of pi is equal to the sine of phi. Cool. Then if we evaluate cosine at pi, I'm looking at -1. Very good.
I think I did it.
I don't see it.
We did that problem for sure. Give me like 2 seconds so I can grab my glasses.
So if I'm looking at pi, I'm looking at half a circle. So yeah, it's going to be,
Cosine's x, it's -1, so
it's going to be -1. Yeah.
Yeah.
So I'm looking at -1 is equal to the sine of phi. So the inverse sine of -1 is equal to phi.
Which is 2.
Cool. So that's how I determine the phase constant. I'm just going to write it as,
Right. Yeah. We did the first one, right?
Yeah.
sine inverse of -1 equals phi. Now the displacement of the particle at t equals 0.25, that's actually really simple to do. All we do is put in a value of 0.25 in the original equation. So you guys can do the math on this. 0.4 meters cosine 3.0 pi times 2.5, or 0.25, my apologies, plus phi, or the phase shift for a cosine. Cool? That's how you would solve for that one. All right?